Rate of change of momentum is directly proportional to force applied on it and moves in the direction of force. The velocity with which the gun moves backward is called recoiling velocity. When two forces are acting at the same plane, when you have two forces, say F1 and F2 are acting at the same plane, then we call it as a coplanar concurrent forces. Hello everyone, I am Nishmananjamma, Faculty of Physics in Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. Welcome back to each one of you for my session 3, chapter 5, Laws of Motion. So in the previous session, we discussed few of the numerical based on the chapter 5. In today's session, we shall study what is linear momentum, conservation of linear momentum, and we shall also study equilibrium of particles or equilibrium of concurrent forces. What we mean by concurrent forces. So to start with, we shall begin the session by knowing what is momentum. We have already discussed many times what is momentum. It is simply represented by P with an arrow above its head, because momentum is a product of mass into velocity. The product of mass and velocity, which gives us a vector quantity momentum. So P is represented by arrow above its head. That is about momentum. Then what do you mean by linear momentum? Linear momentum is the product of vector quantity. It's a product of mass into velocity. Then we also have angular momentum. What do you mean by angular momentum? Angular momentum we study in rotational mechanics. It's a quantity of rotation of a body. We study the law of conservation of angular momentum when we study rotational dynamics. So in this session, we'll study the same law of conservation of linear momentum. So momentum is what? It's the product of mass into velocity. So linear momentum, we are studying about linear momentum. When we study angular momentum, we'll talk something about rotation. So we study angular momentum in rotational dynamics. So what do you mean by the statement? Conservation law states that the total linear momentum of an isolated system remains constant. The total linear momentum of an isolated system remains constant. So the total linear momentum of an isolated system of interacting particle is conserved. What do you mean by isolated system? It's a closed system. What do you mean by isolated system? There will be no interaction or exchange of force between the system and the surrounding. There will be no interaction and exchange of force between the system and the surrounding. For example, if consider you have a jar, closed with a piston, You have a lot of gas molecules inside a jar. It is tightly closed by the piston. Now what happens? The reactions of the gas molecules take place in this jar, which is closed with piston. So these gas molecules interact only within this system. So there will be no exchange of particles or force within this system and the surrounding outside. Whatever happens will be within this system itself. There will be no interaction or exchange of particles or forces with the system and the surrounding. That is what we call isolated system. No exchange of force or interaction of force between the system and the surrounding. Whatever happens to the particles or the gas molecules will be within that particular system. It will not have any connection or connectivity between the surrounding. We say certain set of people are isolated from the society. It is like that. So that is the meaning of isolated system. So the total linear momentum of an isolated system of an interacting particle is conserved. We have Newton's cradle. We have Newton's CRADLE, we have Newton's Cradle, which work on the principle of law of conservation of linear momentum. The principle states that the total momentum before collision and total momentum after collision is conserved. The total momentum before collision is equal to total momentum after collision, that the total momentum of the system is conserved. We have Newton's Cradle where we have a ball. We have many metal balls which are connected to the rigid support with the help of thin wires. With the help of thin wires, we have a rigid support for which the many metal balls are connected with the help of thin wires. So this is a Newton's Cradle. So in Newton's Cradle, when you pull one of the metal ball of the Newton Cradle, it gains some momentum because it has mass and velocity. It has mass and velocity. It will gain some momentum and will hit the second ball in the Newton's Cradle, which is motionless. So when it hit the second ball, the first ball comes to rest. When the first ball comes to rest, that means whether its momentum is lost? No, it transfers its momentum to the second ball in Newton's Cradle, and the second ball transfers to the third ball, and third ball transfers to the fourth ball, and the fifth ball will swing in the air with the same momentum as the first ball, So you can witness the conservation of momentum. You can witness the conservation of momentum when the fifth ball swings into air with the same momentum as the first ball in Newton's Cradle. So when you pull one ball at one end of the Newton's Cradle, this is Newton's Cradle, you'll pull one ball from its end. When you pull and release, it will gain some momentum because each ball has mass and velocity. When you pull, it will gain some momentum. When you release, it hit the second ball. So the first ball comes to rest. That doesn't mean its momentum is lost. Its momentum is transferred to the second ball. The second ball was motionless, but when first ball hit, it will transfer its momentum. The second ball will come into motion, and the second ball will hit the third ball, and third ball in order hit the fourth ball, and fourth ball in order hit the fifth ball. Though the fifth ball will swing in the air with the same momentum as the first ball. So that will show you the conservation of momentum, the total conservation of the system. The total momentum of the system is conserved. When the fifth ball swings in air, again it will hit the fourth ball. Again it will transfer its momentum. Fourth ball will hit the third ball. The reverse chain reaction you can observe. So this is an example. Newton's Cradle is an example which explains the principle of conservation of linear momentum. When you pull one ball, so you will release this ball, but the momentum which the first ball has gained is transferred to the second ball. It is not lost when first ball comes to rest. It is transferred to the second ball, which was motionless. Then the third ball, it was motionless. The second ball will transfer its momentum, and the third ball will transfer its momentum to fourth ball, and so on. It continues. When will you witness this conservation of momentum? When the fifth ball swings in air with the same momentum as the first ball. You can see how the conservation of linear momentum principle is explained using Newton's Cradle, which is beautifully picturized in this video. So next, you can see here, consider an isolated system. You got to know what is isolated system. So the mutual forces between pair of particles can cause change in momentum. The mutual forces between the pair of particles. You're pulling one ball and you're releasing it. So it is transferring its momentum to the second ball, which was motionless, and the second ball will transfer its momentum to the third ball. So the particle can cause change in momentum in individual particles. The momentum change cancels in pair, therefore the total momentum remains unchanged. The total momentum remains unchanged. So next we shall derive an expression for law of conservation of momentum, where we'll prove that the total law of conservation of momentum before collision is equal to conservation of momentum after collision. We'll prove that in this derivation. We will show that the conservation of momentum before collision is equal to conservation of momentum after collision. So for me to derive the expression, I'll make some consideration. And I'll deduce the expression using Newton's third law and then using Newton's second law. So have a quick recap of what is Newton's second and Newton's third law, which I have already explained in session 1 of chapter 5. Please go through that. So let us make some consideration. For example, consider a body A. Consider a body A. It has mass m1. It has mass m1 and velocity v1. Consider a body A. It has mass m1 and velocity v1. So the initial linear momentum. So the initial linear momentum for body A is equal to, which is represented by, initial linear momentum is represented by PA is equal to m1 v1. Consider the initial velocity. I initially take it as it is u1. Similarly, consider body 2. Consider body B, that is body B. It has mass m2 and velocity u2. So the linear momentum, initial linear momentum for body B is equal to, represented by PB. Initial linear momentum for body B is equal to m2 u2. It's a vector quantity. Momentum and velocity are vector quantity. Similarly, this is before collision. After collision, say you have two bodies, say A and B. So initially, the mass and velocity of A is m1, u1, m2, u2. This is before collision. After collision, what will happen? After collision, they will collide. So this be FBA and this is force of collision. So after collision, they will again move apart with velocity v2 and v1. A and B will collide and separate, move apart with velocity v1, v2. Mass is same. Mass is m1 and m2. So after collision, for body A, the final linear momentum is represented by P dash A. P dash A is equal to m1 v1. So for body B, the final linear momentum will be PB dash is equal to m2 v2. PB dash is equal to m2 v2. Now consider I have a body A and body B which are moving with mass m1, m2 and velocity u1, u2. So the initial linear momentum for body A will be given by PA is equal to m1, u1. Similarly for body B, the initial linear momentum that is before collision for body B will be PB, m2, u2. Similarly after collision, initially before collision, after colliding After colliding, they move apart with velocity v1 and v2. So after collision, the final linear momentum that is given by PA dash will be m1 v1, and for body B, final linear momentum will be PB dash is equal to m2 v2. m2 v2, initially it was u1 u2, after collision it is v1 v2. Now, using Newton's third law, what does Newton's third law say? Every action has an equal and opposite reaction. Every action has equal and opposite reaction. So using Newton's third law, I will deduce the expression for law of conservation of linear momentum. I'll deduce the expression for conservation of linear momentum. Next, I'll write this as PA dash minus PA by delta T is equal to minus of PB dash PB by delta T. How did I get this expression? How did I arrive at this relation? Using second law. Using Newton's second law of motion. What does Newton's second law say? It is change in momentum. Rate of change of momentum is directly proportional to force applied. Rate of change of momentum is directly proportional to force applied on it and moves in the direction of force. So, using this second law, I have written this relation. So, what is this? Change in the final linear momentum of body A minus change in the initial linear momentum of body A divided by time taken is equal to change in the final momentum. Change in the final momentum of body B minus change in the initial momentum of body B divided by delta T. What happens? Delta T gets cancelled. What is remaining? PA dash minus PA is equal to minus PB dash minus plus PB plus PB. Shifting the terms, you will get PA dash plus PB dash is equal to, negative goes to this side, it will be positive. So, PA plus PB. PA plus PB. What is the value of PA dash? After collision, M1 V1 plus M2 V2 is equal to, what is PA now? Before collision, M1 U1 plus M2 U2. So, I can say the total momentum of the system is conserved. So, the change in momentum, the final change in momentum of body A plus final change in momentum of body B is equal to initial change in momentum of body A plus change in momentum of body B. So, they are equal. So, what I can say? The total momentum of the body is conserved. I can say total momentum of the body is conserved. That is, total momentum before collision is equal to total momentum after collision. Total momentum before collision is equal to total momentum after collision. So, this is how we proved the law of conservation of linear momentum using Newton's third law and Newton's second law. So, this is the law of conservation of linear momentum. I hope you all have understood, got a clear picture about the law of conservation of linear momentum. So, considering two bodies A and B with mass m1, m2 and velocity u1, u2 before collision. So, the initial linear momentum for body A will be given by PA, momentum of body A is equal to m1 u1, and for body B it is m2 u2. So, after collision, after they collide, they move apart with velocity v1, v2. Mass will be m1 and m2. So, after collision, the body A is equal to final linear momentum will be given by PA dash, PB dash for body B. PA dash will be M1 V1, PB dash will be M2 V2. So final total initial linear momentum, total initial linear momentum will be PA plus PB, vector PA plus PB, because momentum is a vector quantity, PA plus PB. So total final linear momentum after collision, total final linear momentum after collision will be PA dash plus PB dash. You can see here PA dash plus PB dash. So before collision, this is after collision. So the total momentum of the body is conserved. So the total momentum before collision is equal to total momentum after collision. This is the principle of law of conservation of momentum. We are considering two bodies with its respective mass and with its respective velocity. Again, we are considering two bodies after collision, what will be its velocity and mass. Next, we are telling that PA plus PB before collision, PA dash plus PB dash after collision. We have proved it here. Momentum is a vector quantity. Velocities are also vector quantity. This is about law of conservation of momentum. You had two bodies with respective mass and velocity. They collide with some force, and after collision they separate out. They move apart with velocity V1, V2. The mass will be M1 and M2. So next we have the illustration. The two boys walking in the road or two people running, Monte Carlo experiment, rocket propulsion, all work on the principle of law of conservation of momentum. So we have few examples for conservation of momentum, illustration for conservation of momentum. The first one is recoiling of gun when bullet is fired. Recoiling. What do you mean by recoiling? Recoiling of gun when a bullet is fired. You can see the first picture here when the bullet is fired. When you fire the bullet from the gun, when you fire, we apply some force and we'll fire the bullet from the gun. What happens? The bullet will come into motion. The bullet will move in forward direction towards the target, but the gun moves backward. The gun moves backward in the direction opposite to the motion of the bullet. Opposite to gun, the bullet is moving in this direction, the gun will move backward. Gun will move backward opposite to the direction of motion of bullet. So that is what we call as recoil. The velocity with which the backward motion of the gun is called recoil, and the velocity with which the gun recoil is called recoil velocity. When both the gun and bullet before firing both are at rest, so the total momentum is zero. When we fire the bullet from the gun, it acquires large momentum and starts to move forward. Same equal and opposite momentum, the gun recoils. The gun moves backward. That is what is the first point telling us recoiling of gun when bullet is fired is an example for principle of conservation of momentum. What happens? The bullet will move forward. It will come into motion. It will move forward towards the target. So when it moves forward, the gun will move backward. The backward motion of the gun is called recoiling. The velocity with which the gun moves backward is called recoiling velocity. When you fire the bullet moves in the forward direction. The gun will move in the backward direction opposite to the bullet. Before the bullet is fired, the total momentum is zero. When you fire the bullet, it will acquire large momentum and move forward with the same equal and opposite momentum. The gun will recoil, gun will move backward. So this is the example, first example. What is second example? When a man jumps from a boat, to the shore, the boat moves backward. When a boy or a man jumps from the boat to the shore, boat moves backward. This image gives you the example of the second point. This image gives a picture of the second point. You can see a man is jumping from the boat to the shore. Boat to the shore. So what happens? The boat will gain equal and opposite momentum and it will move backward. It will move backward. This is the reaction. Before the man starts to jump, both the boat and the man is at rest. When the man starts to jump from the boat, it will acquire large momentum. So the boat will move with the same and opposite momentum to the backward. So before jumping from the boat, the total momentum was 0. When the man jumps from the boat, it acquires equal and opposite momentum, because of which the boat moves backward. So when a man jumps from the boat to shore, what happens? The boat will move backward. Why? Because before the man jumps, the boat will be at rest. The boat will be having 0. The total momentum will be 0. So when the boy starts to jump, the boat will acquire equal and opposite momentum. So it will move backward. So that is the second illustration for conservation of momentum. What is the third point? What is the third point? Is very important. The principle of rocket propulsion is based on the conservation of momentum. The principle of rocket propulsion is based on the principle of conservation of momentum. So what is this? See, this third image gives you a picture, clear picture about the third point, which states that principle of rocket propulsion is based on the conservation of momentum. So this is the head of the rocket. This is the tail of the rocket, and in the rocket you have this propellant chamber. This is a fuel. This is a fuel chamber. When combustion of fuel takes place, when the propellants are burnt, large amount of gas are ejected from the tail, with high velocity. The large amount of gas are ejected with high velocity with large momentum. So which in turn the rocket will move upward, gaining large momentum. When the fuel chamber, the propellants, you have propellant chamber where fuels are burnt. When combustions occur, large amount of gas are ejected from the tail, which gases are moving downward with high velocity, having large momentum. So because of which the rocket moves up towards the outer space with the same equal and opposite momentum. Thus, the rocket will move upward with the same change in momentum as that of ejected gas. The rocket will move upward with same change in momentum as that of ejected gas. As that of ejected gas. So this is the principle. Of rocket propulsion, which is based on conservation of momentum. When gases are ejected, it moves downward with large momentum, with high velocity. The mass will change. The mass is not constant. In Newton's second law, we studied mass is constant. But when it comes to rocket propulsion, the mass is not constant. We'll have variable mass. So in case of rocket propulsion, rocket launching, the mass is not constant. So there will be variable mass. So again, we have to question Newton's second law of motion, which says mass is a constant. But when it comes to this rocket propulsion, mass is not constant. We have something called variable mass, m. So that questions the Newton's second law of motion. In the upcoming sessions, we'll detailedly discuss about the variable mass, where Newtonian second law is questioned. That is when the Einstein came up with the special theory of relativity. When this variable mass, when Newton's second law was questioned in classical mechanics. We'll study that in detail in your higher classes. So these are the examples for conservation of momentum. So next you have equilibrium of concurrent forces. Equilibrium of concurrent forces. What do you mean by the term equilibrium? What is equilibrium means? It is nothing but the net external force acting on the system is equal to 0, Suppose you have two bodies moving with some force in the opposite direction. Force is a vector quantity. They'll have same magnitude but opposite direction. So they'll cancel off. The net force of the system will be equal to 0. If the net force is equal to 0, we say it is in equilibrium state. Equilibrium state. Or when the object is at rest or in uniform motion, does not change when an external force acts on it. When there is no change in state of rest or uniform motion of a body, when a force acts on it, then the body is called equilibrium. Then the body is said to be in equilibrium. When there is no change in the state of rest or uniform motion, when it's acted upon by a force, when a force acts on it, the body is said to be in equilibrium state, equilibrium condition. Net force is equal to 0. Net force is equal to 0. So here we have concurrent forces. So what do you mean by concurrent forces? Many forces acting at the same point of the object. So I have an object here. So many forces are acting at the same point of the object. F1, F2, F3. So many forces are acting at the same point of the object. That is called concurrent forces. A number of force acting at the same point on an object is called concurrent forces. Concurrent forces. In the concurrent forces, many force will pass through the common point. In a concurrent force system, many forces will pass through the same point. You can see in concurrent force system, many forces are passing through the common point. That is what we call concurrent forces. Then what do you mean by coplanar concurrent forces? What do you mean by coplanar? We have studied in our chapter 3 in the previous sessions when we discussed about the types. What is coplanar? When two forces are acting at the same plane, when you have two forces, say F1 and F2 are acting at the same plane, then we call it as a coplanar concurrent forces. When two or more forces are acting on the same plane, we call it as coplanar concurrent forces. So what is concurrent forces? The forces which are acting at the same point of an object. The number of forces acting at the same point of the object. In concurrent force system, the forces, many, 1, 2 or 3 or more forces passing through a common point, we call it as concurrent force system. So what is the requirement for a particle to be in equilibrium? The resultant, the net force should be equal to 0. Suppose consider I have two forces F1 and F2. I have two forces F1 and F2. For what is the requirement for equilibrium of particle? The resultant, the net force acting on particle should be equal to 0. When it is equal to 0, I can write F1 is equal to minus F2. What does it say? The two forces are acting equal and opposite to each other. Suppose consider I have F1, F2, F3 up to Fn number of forces acting on the same point of the object. The forces are passing to the common point of the object. It is a concurrent force system. So what is the condition for concurrent force system? For it to be in equilibrium, the resultant of the force must be equal to 0. The vector sum of concurrent forces. So this is a concurrent forces. The forces which are passing through the same point of the object, which are passing through. Suppose I have an object. These forces are passing through the same point of the object. I have F1, I have F2, I have F3, I have F4. Similarly, I have Fn number of concurrent forces. So what is the requirement for the particles to be in equilibrium? The vector sum of, because it has both magnitude and direction. So the vector sum of concurrent forces must be equal to 0. Then we say that it is in equilibrium. It is in equilibrium. F1 so on up to plus Fn is equal to 0. This is a requirement for equilibrium. The vector sum of concurrent forces is equal to 0. Then we say the system of particle is in equilibrium. Suppose consider I have 3 forces, F1, F2 and F3. It's a vector. Force is a vector quantity. I have 3 forces. What I'll do? Consider it is a concurrent force. Concurrent force, I have a particle. Consider I have 3 concurrent forces which are passing through the common point. That is, I have an object which is acted upon by 3 forces at the same point. It is acted upon by the 3 forces F1, F2, F3. It is acted upon by 3 forces at a common point, at the same point of the object. So these are the 3 concurrent forces. So these are the 3 concurrent forces. What is the requirement? If I say this as O, this as B, this as A and this as C. So what is the requirement for it particle to be in equilibrium? Their net force should be equal to 0. That is F1 plus F2 plus F3 is equal to 0. Requirement for equilibrium of particle is concurrent forces. The sum of concurrent forces must be equal to 0. Must be equal to 0. Suppose, see, I have 2 sides which are intersecting at a common point. So, I will build a parallelogram. I will complete a parallelogram to explain this concurrent forces, because I have 2 adjacent sides meeting at a common point from where I will draw the diagonal, say C dash. I will draw a diagonal, say OC dash. So OC dash, if F3 is positive, then this OC dash will be negative. It will be negative. If you have x-axis in the number system, if you say this will be your negative x-axis. If you have 1, 2, 3, then the negative will have -1, -2, -3, right? Similarly, if this has positive F3, then the diagonal which is equal and opposite to OC, that is OC dash, will have negative of F3. So, how will you obtain the resultant? In case of parallelogram law, the diagonal will give you the resultant, right? The diagonal OC dash is equal to OA vector plus OB vector. OC dash is equal to OA plus OB. Diagonal, the resultant is given by diagonal in parallelogram law. We have discussed in the previous sessions. The diagonal is equal to the resultant of 2 adjacent sides of the diagonal. So what is the resultant? OA, it will be F2 plus F1. F2 plus F1. Then what is OC dash? OC dash is equal and opposite to OC, but the sign is negative. It will be minus F3. So F1 plus F2 is equal to minus F3. That means that 2 forces are equal and opposite to the third force acting on the particle. That is, the resultant of 2 forces F1 and F2 must be equal and opposite to the third force F3. The resultant of two forces must be equal and opposite to the third force. Similarly, I have seen here two forces, say F1 and F2, are equal and opposite to each other, This is equilibrium of concurrent forces. What is equilibrium? The net force acting on the system is equal to 0. For the requirement for the particle to be in equilibrium, what is the requirement for a equilibrium of particles? Net forces should be equal to 0. Here we are talking about the concurrent forces. What is concurrent forces? 1, 2, 3 or n number of forces which is acting at the same point, of the particle or system is called concurrent forces. If two forces are acting in the same plane, then we call coplanar concurrent forces. Next, we analyzed it using this diagram. See, this is a parallelogram that I have created to derive the expression in terms, to derive the resultant in terms if you have three forces. If you have two forces F1 and F2, what is the requirement for it to be in equilibrium? The net force, the sum of concurrent forces must be equal to 0. Then I take F1 is equal to minus F2. When I take this to RHS, it will be F1 is equal to minus F2. What do you mean by that? That two forces F1 and F2 are equal and opposite to each other. Similarly, what will happen if you have n number of forces, n number of concurrent forces which are passing through the same point of the object? For the requirement for the equilibrium condition, the requirement for it to be in equilibrium is the vector sum of the concurrent forces must be equal to 0. Then we say it is in equilibrium. That is the requirement for the particle to be in equilibrium. So, similarly, if I consider three forces, I'll complete a parallelogram to explain the three forces, the equilibrium state of three forces in the system. So, when I draw a parallelogram, in parallelogram the diagonal gives the resultant vector. So, the diagonal is equal to sum of two adjacent sides. So, you can see the resultant vector is equal to 0. That means that's the requirement for equilibrium state. So, the concurrent forces are in equilibrium. So, when I take the resultant is equal to two adjacent side, I can see minus F3 is equal to F2 plus F1 or F1 plus F2 is equal to minus F3. That means the resultant of two force is equal and opposite to the third force F3. So, this is about the equilibrium of concurrent forces. That's all for today's session. We discussed the conservation law, the law of conservation of linear momentum. We studied Newton's cradle, how momentum is transferred from one ball to another ball, and we have seen how the conservation law works, how Newton's cradle is explained with the principle of conservation of momentum. Next, we derived the expression and we proved that total momentum before collision is equal to total momentum after collision. In an order, total momentum of the system is conserved. Next, we studied the examples which work on the principle of conservation of momentum, illustrations of conservation of momentum. A man jumping from the boat to the shore. Next, the rocket propulsion, which work on the principle of linear momentum. How they gain equal and opposite momentum and they starts to propagate in the forward or backward direction. Next, we studied the equilibrium of concurrent forces. So, equilibrium means the net external force is equal to 0, that the magnitude and direction equal and opposite, they cancel out. Next, we studied the concurrent forces, number of forces acting at the same point of the object, passing through the common point is called concurrent forces. Further, what is the requirement condition for it to be in equilibrium? The vector sum of the concurrent forces, the net force concurrent forces must be equal to 0, F1 is equal to minus F2. Two concurrent forces are equal and opposite to each other, Similarly, this is in case of three concurrent forces. So next, I'll be coming up with more interesting session where we'll discuss about frictions in the upcoming session of laws of motion. Until then, take care. Have a good day. Thank you.